Welcome to this chapter on time series analysis and forecasting. Here we learn how to read data that arrives in time order and how to use the past to predict the future. Picture a power company watching its control room screens on a winter evening, in effect betting on the future. Observations stamped with the time they were recorded and read in order are called a time series, and we will build up the toolkit step by step. By the end of this chapter, you should be able to explain what time series data is, why its order carries information, identify trend, seasonality, cycles, and noise, understand stationarity and differencing, and apply moving averages and exponential smoothing. You should also be able to explain the intuition behind autoregressive, moving average, and ARIMA models, evaluate forecasts with several error metrics, split time series data correctly, and engineer features for machine learning models. This figure shows time series decomposition. We pull an observed series apart into a long-run trend and a repeating seasonal pattern, and whatever is left over is the residual. Seeing the pieces separately makes the structure much easier to understand. Let us define our subject. A time series is a sequence of observations recorded in time order, where each one is tied to a specific timestamp, and the order of the observations is itself part of the information. The defining feature is that order matters. Once you start looking, you meet time series everywhere: daily stock prices, monthly revenue, hourly electricity demand, and weekly patient arrivals at a hospital. The list keeps going. Minute by minute traffic to a website or vibration and temperature readings streaming off factory machines are all time series too. Forecasting means using what we have already seen to predict what we have not. The decisions it supports span almost every part of an organization. Think of inventory and replenishment, staffing and shift scheduling, budgeting and financial planning, capacity and infrastructure investment, energy generation, and supply chain coordination. Every one of these rests on a forecast. And here is a comforting point. A forecast does not have to be perfect to be worth having. Even a rough estimate beats flying blind. To understand a series, it helps to imagine it as several simpler patterns layered on top of one another. There are four such layers. Trend is the long, slow drift up or down. Seasonality repeats on a fixed calendar. Cyclic behavior swings on a looser schedule. And noise is the irreducible random wiggle left over. Naming these components is not just an academic exercise. Knowing which pattern is which tells us how to model the series and what to expect from it. Let us take the components one at a time. A trend is the long-term direction of a series, the movement you would still see if you squinted past the month-to-month jitter. Seasonality is the part of a series that repeats on a regular calendar, like higher ice cream sales every summer or heavier traffic every Monday morning. Cyclic behavior also rises and falls, but on longer and looser schedules than seasonality. Business cycles are a classic example, real but not tied to a fixed calendar. Finally, whatever is left after trend, seasonality, and cycles is noise, random variation with no pattern we can exploit. Recognizing it keeps us from chasing patterns that are not there. Now, to a key idea. A time series is weakly stationary when its statistical character stays put over time. Its mean, its variance, and the way each observation correlates with earlier ones do not drift as the series unfolds. Stationarity matters because many classical models, ARIMA above all, simply assume it. So, before fitting them, we often need to make a series stationary first. Differencing replaces each value with how much it changed from the previous step, much like turning elevation into climb rate. If the original series drifts steadily upward, the difference series hovers around a stable level, much closer to stationary, and this is the integrated part of ARIMA. This figure shows why differencing helps. The original series on top drifts steadily upward, so its mean keeps changing and it is not stationary. The first difference below strips out the trend and hovers around a constant level. A moving average smooths a series by replacing each point with the average of itself and a few neighbors. Averaging blends away short-term noise and lets the trend show through, which makes it mainly a tool for seeing a series clearly rather than forecasting far ahead. Exponential smoothing keeps the smoothing idea but adds a sensible bias. Recent observations should count for more than ancient ones. A smoothing parameter between 0 and 1 controls how quickly the influence of older values fades away. The Holt-Winters method stretches exponential smoothing to cover trend and seasonality, tracking three quantities at once: a level, a trend, and a repeating seasonal pattern. It comes in three flavors of growing richness: level only, which is simple exponential smoothing; level and trend, known as Holt's linear method; and level, trend, and seasonality together, the full Holt-Winters. For business series with a clear and stable seasonal shape, like monthly sales or hourly load, Holt-Winters is often a strong, low-fuss baseline that is hard to beat. An autoregressive model says, in effect, that the recent past predicts the present. Today's value is built from yesterday's value, scaled by a coefficient plus a constant and some random error. A moving average model takes a different angle. It predicts the current value from past forecast errors rather than past values. The current value depends on the series mean plus a blend of recent random shocks. How do we decide how far back an autoregressive or moving average model should reach? Two diagnostic plots, the ACF and the PACF, are the classic fingerprint for choosing the orders. This figure shows the ACF and PACF for an autoregressive process of order 1. The ACF tapers off gradually, while the PACF shows one strong spike at the first lag and then drops inside the noise band, the telltale signature of that model. AHIMA, short for Autoregressive Integrated Moving Average, folds the three ideas we have met into a single framework. Its three parts are the autoregressive terms, the dependence on past values, integration, the differencing that makes the series stationary, and the moving average terms, the dependence on past errors. A model is written as a REMA of P, D, and Q, where P is the autoregressive order, D is the number of differences, and Q is the moving average order. A key point before reaching for anything sophisticated: fit a simple baseline like carrying the last value forward or repeating last year's same month. Many advanced models quietly fail to beat these, and a forecast is only as good as the margin by which it improves on the obvious guess. The classical Box-Jenkins procedure for fitting an ARIMA model is summarized in the next figure. Here is that procedure laid out. Check stationarity, difference if needed, identify the orders from the ACF and PACF plots, fit the model, check the residuals, and then forecast. It is a disciplined loop rather than a single shot. A forecast must be judged on data the model did not see while fitting. Mean absolute error reports the typical miss in the original units, while root mean squared error squares the errors first, so it punishes large misses far more harshly. The three error metrics look interchangeable on the page, but they can rank the same two models in opposite orders. The only way to really feel that is to compute them. Consider 5 held-out months and 2 models. Model A is off by 10 every single month. Model B is perfect for 4 months but misses the fifth by 40, a stock-outsized blunder. The two models have opposite personalities. One is steadily mediocre, the other nearly perfect with one disaster. Let us see how each metric scores them. Averaging the absolute errors, Model A scores 10 since it is off by 10 every month, while Model B scores 8. By mean absolute error, Model B looks better. Root mean squared error squares the errors first, so one large miss counts for far more than several small ones. Model A scores 10, but Model B's single error of 40 pushes it to about 17.9. Now Model A wins. Mean absolute percentage error expresses each miss as a fraction of the actual value. Here, Model A comes out near 10.2% and Model B near 10.0%, an almost tied result that tilts slightly toward Model B. Same data, three metrics, and no consensus. Mean absolute error and percentage error favor model B, while root mean squared error favors model A. The metric you choose encodes what kind of mistake you fear most. This figure plots the two forecasts against actual demand. Model A misses by a steady 10 every month, while Model B tracks the truth exactly until month 5, where it overshoots badly. You can see at a glance why squaring the errors changes the verdict. In the supervised learning of earlier chapters, we shuffled the data and split it at random. With time series, that approach quietly breaks because shuffling lets the model peek at the future. A single train test split tells you how the model did on just one slice of the future. To trust it more, we need to test it repeatedly across many points in time. Walk-forward validation does exactly that. Train up to a point, forecast the next step, reveal the true values, and fold them into the training set, refit and forecast again, and keep marching the origin forward through the series. This mirrors how a forecasting system actually lives. Every day or week, new data arrives and the model updates. Walk-forward validation tests the model the same way reality will. Here is the pivot that lets the whole machine learning toolbox loose on forecasting. We turn the series into a table of features so any regression model can learn from it. The useful features come in several families. Lag features like the value a week or a year ago, rolling statistics over recent periods, calendar features such as day of week and month, event markers like promotions, and cyclical encodings of time. A lag feature simply feeds yesterday's value in as an input column, letting the model lean on it exactly as an autoregressive model would, but inside a general regression. Some calendar features are circular, and naive encoding gets them wrong. By encoding the month with a sine and a cosine, December and January land right beside each other, so the model learns smooth yearly patterns instead of tripping over an artificial cliff between month 12 and month 1. Once the features exist, forecasting becomes ordinary regression. We build lag and rolling features, add calendar and cyclical ones, split by time order rather than at random, train on the past, and evaluate on held out future data. The strength of these methods is flexibility. Their cost is that they demand careful feature engineering and scrupulous validation. Sloppiness here quietly lets the future leak into the past. When the data is large, the patterns are intricate, or many related series must be forecast together, deep learning enters the picture, including recurrent networks and their gated variants, temporal convolutional networks, and transformer-based forecasters. These models can learn long-range dependencies straight from the raw sequence, but they are hungry for data and compute and easy to over-engineer. It is also worth knowing Profit, a library built for business forecasting that decomposes a series into trend, seasonality, and holiday effects. Forecasting is humbling because the future is not obligated to resemble the past. We face missing and corrupted readings, one-off outliers, drifting seasonal shapes, abrupt structural breaks, and the slow erosion of old patterns known as concept drift. There are also external shocks like a pandemic or a policy change, and sometimes simply too little history to learn from. A model trained on years of pre-2020 demand was blindsided when lockdowns reshaped behavior overnight. No architecture rescues a model when the world itself changes. Let us move to Python. We start with a genuine seasonal series, real airline passenger data rather than a synthetic one. This code loads the classic monthly airline passengers dataset, builds a proper date index, and plots the series so we can see its rising trend and its strong yearly seasonality with our own eyes. Before modeling, we can pull the series apart into its components and smooth it to bring out the underlying trend. This code performs a seasonal decomposition into trend, seasonal, and residual parts, and then adds two moving averages over 3 and 12 months. The plots make the layered structure of the series explicit. The decomposition splits the series into separate trend, seasonal, and residual panels, making the structure we discussed earlier visible at a glance. Now we fit a seasonal ARIMA forecast with stats models evaluated honestly on a held-out tail of the series. This code holds out the last 24 months, fits a seasonal ARIMA model with a yearly season, forecasts the held-out period, reports the error metrics, and plots the train, test, and forecast curves together. Because this series has obvious seasonality, the seasonal orders really matter. A plain ARIMA with no seasonal terms would miss the yearly humps badly. Next, we take the supervised learning route. We turn the series into a feature table and let a random forest forecast it. This code builds lagged features at 1, 2, and 12 months plus a rolling mean, splits the data in time order without shuffling, trains a random forest, and reports the error metrics on the held out months. The lag 12 feature is what lets the tree pick up the yearly cycle because it hands the model the value from the same month a year earlier. Finally, we build the circular encoding of the month, ready to drop into any of the machine learning models above. This shortcode computes the sine and cosine of the month and prints the first 13 rows so we can inspect how the calendar gets turned into smooth circular coordinates. Printing 13 rows confirms the wraparound. December's sine and cosine sit right next to January's, exactly the closeness the model needs to treat the year as a loop rather than a line. Now a case study. A regional grocery chain runs a few hundred stores and tens of thousands of products, and for each one it must forecast next week's demand. Forecast too low and shelves go empty. Forecast too high and perishables spoil, while cash sits frozen in inventory. The stakes pull in both directions at once, which is what makes the problem interesting. Their workflow looks like the chapter in miniature, and for modeling, they do not crown a single winner, but combine several approaches. The code below fits a simple ARIMA model to log transformed monthly airline passenger counts, a compact stand-in for the seasonal demand series the grocery chain works with. This code loads the flight's data as a proxy for demand, takes a log transform to stabilize the variance, fits a simple ARIMA model, prints the AIC and BIC scores, and produces a 12-month forecast that is converted back to the original units. Printing AIC and BIC lets practitioners compare this specification against alternatives, while back transforming the log scale forecast returns values in the original units that operations teams can actually act on. To summarize, time series data is ordered by time, and that order is information, not decoration. We covered the classical toolkit from stationarity and differencing through moving averages, smoothing, and the ARIMA family, and then the modern machine learning route. For further reading, the freely available Forecasting Principles and Practice is excellent, along with the stats models documentation on ARIMA, the Pandas documentation on time series, the profit documentation, and applied case studies in retail, energy, and healthcare. For the statistical learning foundations behind the machine learning pipeline, including regression, regularization, and ensemble methods, the text by Hastie, Tibshirani, and Friedman is a thorough companion. That brings us to the end of Chapter 20, where we learn to read the past in order and use it to forecast the future.